Okay, so today we're going to continue our exploration of hidden Markov models, HMMs, and then we'll look at one of their primary applications, which is speech recognition. So what were Markov models? Markov models were models of this type over here. You had a state at time 1, which we denote by the random variable x1 because we don't know what the state value is or is going to be. Then there's x2 for time 2 and so forth. It could be whether it's raining or sunny at on a certain day. You have two conditional probability tables to define your model. The first one defines the initial distribution, and this one defines the transition model. You could redraw your transition model, which is just a conditional probability table, into a graph like this, which is sometimes useful to expose the structure of the conditional probability table. We'll start using this when we do speech recognition to expose the structure of the conditional probability tables inside the speech recognition models. Then another example of Markov model that we looked at is a hidden Markov model. What you have here is you still have the sequence of states, but typically the assumption is that you have another sequence of variables, which are the evidence variables, which you actually get to observe. And you try to infer what the state variables are from the evidence variables. And the way you tend to do it is you run probabilistic inference in this Bayes net, which is a Bayes net that keeps going on and keeps growing as time goes by, to find a distribution over the state variable at the current time, which you would call the belief at the current time, given all evidence observed so far. So the example we had there was it could be raining or it could be sunny. You never get to look outside, but every now and then your professor comes by and has an umbrella or doesn't have an umbrella, and that allows you to run inference and infer without ever having seen outside what the weather might be like today, next day, and so forth. Okay, let's do a little quiz here on Markov models. Two questions. So the setup is that we have a ghost. We don't know where the ghost is, but we have an initial distribution, which is shown over here. So most of the probability mass is over there. The first question is, if the ghost moves randomly, let's say equally likely in all directions, as time goes by, what will the distribution look like for where the ghost might be? Question 2 is, if the ghost moves towards the square with coordinates 3, 3, what happens as time goes by? What do you think for quiz 1? Any thoughts? Yes, over there. So the suggestion is that as time goes by, even though it's just a Markov model and we don't have any measurements, some process will happen and we can run inference in our heads of what might happen. And we think of what the stationary distribution might be, right? And without knowing the specifics of the numerics of the model, if the ghost moves randomly, this probability mass would disperse over all the possible states. And you'd have something close to a uniform distribution over all possible grid squares. That's what typically happens if you have a model with a lot of randomness. How about the second case? Well, it's saying it. The ghost is always moving towards 3, 3. Thing to keep in mind is that while we model this as a distribution, the ghost knows where they are. The ghost actually takes an action and can move towards 3, 3. If we have a model that captures this, we know that no matter where they started, they'll converge onto 3, 3. And what you get is a distribution where all the probability mass is sitting right here at time t equal infinity, maybe even sooner. Everything will have converged to that particular square. Everything else will be 0. And so what we see is that as time goes by, again, we go to a stationary distribution. But this time, the stationary distribution is such that all the mass is in one particular state. So one thing to keep in mind that both are possible. The first type of situation is a noisy, maybe unstable system where the probability mass spreads out. The second type of system is a stable system where there are particular states that attract and where the probability mass tends to agglomerate into those states. So both are possible. Okay, then we said, well, usually it's not the situation where we just, based on the model, have to predict where the ghost might be in the future. We get measurements. We use a sensor. That's the hidden Markov model situation. And the way we run inference then is this way here. We, at a given time, have knowledge of this distribution here, which we have also called bt minus 1 for xt minus 1. Then when time goes by, we make an update to that distribution. We account for the transition probabilities, which are stored in this model over here. And so essentially just count for every possible state at time t minus 1. What's the probability of being there, stored over here. Multiply that with the probability of going into a new state, xt. Sum that all together, and that gives us the probability of being in state xt, given all evidence we've seen up to time t minus 1. Then when the measurement comes in, we say, well, the likelihood of a particular state now has to be multiplied with the likelihood of the evidence. After multiplying that in, really what we get on the left here is the probability for what we had before, xt minus 1, given e1 through t minus 1, jointly with et. No, there's wrong index here. This is what we get. Now, what we're interested in is conditioned on all the evidence, so we want to move this guy behind the conditioning bar. Since that's not a variable, it's a fixed value at the time we observe it. All we need to do is renormalize, so we look at all values that we get for every different instantiation of xt, sum them together, and divide every value by that. Now you have a normalized distribution, and you get this thing over here. So the computations are fairly straightforward, and these repeat just over and over and over at every time step. Question? Yes? Let's see. The subscript over here. Here. Okay. B t over, let's say, xt is equal to, by definition, it's just a shorthand notation for the distribution for xt given evidence from time 1 through time t. So just a shorthand notation for that particular distribution. Okay, we could apply this to the example where we get to not observe directly whether it's raining or sunny, but you get to see an umbrella or not to see an umbrella. And maybe at time 1, the distribution is 50-50. That's your prior. Then time goes by. Let's see. First thing that happens is you get to see the professor with the umbrella. You do an observation update, which is this one over here. This gives you a new distribution. You saw the umbrella, so now rain has become a lot more likely. Time goes by. You now have a diffusion because it tends to transition from rain into sun fairly likely and the other way around. So you get a diffusion here closer to the uniform distribution. Then when a new measurement comes in this case, again umbrella, we again do the update, and again it goes closer to lots of mass on rain. Okay, that's just a simple example to illustrate what could be happening. What we're going to look at now is something that will solve the same problem, but when the state space is a lot larger. So far, we've looked at these kind of toy examples, very small state spaces, and we can do these computations exactly. What we're interested in going forward is state spaces where this computation would be too expensive. You wouldn't be able to do it in a reasonable amount of time, as fast as time goes by, because you want to keep track of things as they happen. And so you want to use something a little more efficient. We'll have very little time left to complete lecture, unless... All right. So the technique we're going to look at is called particle filtering. The interesting thing is that it's actually something simpler to implement than what we already looked at, and it can be faster for large state spaces. So it's a great technique to be working with. The downside is it's a sampling technique, so it's not exact, it's just approximate, but the more samples you're willing to use, the more accurate it'll get. Okay, so just pictorially, what will our representation now be like? Instead of having a distribution over where the robot might be, we'll just have a bunch of pins saying robot might be here, might be here, might be here. And that's a new way of representing the distribution over where the robot might be. So it's not a traditional distribution, it's just a distribution represented by a bunch of particles, is what we'll call them, sitting at certain locations. Okay, so let's look at what we want to do here. We have a distribution. One thing to keep in mind that this is a toy example, right? Just 9 states. You have to have a very poor implementation to not be able to keep up with updates with just 9 states. Just to illustrate the concept, when you want a particle filter, typically you'll have infinitely many states that are possible, or maybe even more than you can represent in memory of your computer. That's when you'll typically use it. But on the slide here, we just have 9 states. And one thing we can do is we can say, instead of representing the distribution as these 9 numbers, we can instead represent the distribution by particles. And if we do it this way, where we drop 1 particle here, 2 here, 5 here, and 2 here, we actually represent the exact same distribution as we had up here, just in a different way. Because if you look at this representation here, you say, what's the probability of the robot being in this square over here? You'd say, well, 0 out of 10 particles are there. So that's 0 over 10, which is 0 probability. If you ask yourself the question, what's the probability of the robot being here? You say, well, 2 of the particles are in that square, 10 total particles, so 2 out of 10 is the chance of the robot being in that particular square. Now, the one important thing to keep in mind, and it's tough to illustrate with these small state spaces, is that state space is really, really large. So rather than having a 2-dimensional array in which you store how many particles are sitting in each entry in the array, you'll have a list of particles. So your internal representation in your computer will be something like this. Just a list, and each entry in the list is 1 particle. Now, I understand this list is 10 long. You might be able to represent that 2D array with the same amount of memory as you can represent this list, but keep in mind that, imagine that is a infinite dimensional state space. You could still represent a list of 10 particles that are in 10 possible locations in that infinite dimensional state space. So this is your actual representation. Not enough space. That you store in your computer. Okay. One example application is you have a continuous state space. There's no way you could have an array that tabulates all possible states, and then having this list of particles is one alternate way of representing the distribution. Another example is where even if you have a moderate state space, maybe the ghost can only be in 100 locations, there are maybe 100 ghosts. And so now the actual state space is 100 to the power 100 because each ghost can have 100 different possible locations. And so you have a very large state space, too large to represent in a tabular way. And so you'd still want to use a particle filter instead of an exact inference algorithm. So we're going to do approximate inference. The key is going to be that we're going to keep track of these particles. So somehow we're going to say we have these 10 particles, and as time goes by and measurements come in, we're going to move these particles into the grid squares that make the most sense in terms of representing the distribution that we're trying to track. This is actually how it works, and we'll see some examples later of this in action for large state spaces. One thing to keep in mind here is that a particle is just a new name for a sample. It's the same thing, it's just that's what it's called. In this context, it's called particle filtering. All right, so the representation is one where we use particles. This is what we store. Sometimes these particles will have weights. These particles don't have a weight next to them, which means they all have equal weight. You can imagine the weight is 1. You can imagine the weight is anything, as long as it's all equal for all of them. All right. Now, when time goes by, what you do in a particle filter is something very, very simple. You just loop through all your particles. So you go through each one of these one at a time. When you look at one of them, you say, let's simulate what could happen if the robot were in the 1, 2 square, which is the one over here. So this particle over here. No, not over there. Wrong readout. Over here, 1, 2. The robot is over there. We have a transition model, which maybe says that the robot tends to move clockwise around this grid. Then we can simulate that. And so we can simulate what would happen. Really, we know that there's a distribution for where the robot could be at the next time. Multiple possible states. We sample from that distribution. And that sample is now what we use over here. So this thing landed over here. Then we go to the next one, 2, 3, which is this one over here. Again, we sample from its distribution, from its transition model. What's the distribution for location at the next time, given the current time location is 2, 3? It'll be some distribution over neighboring squares. You sample from that distribution, and in this case, we landed at 3, 3, which is over here. And so we work through the list of particles, one particle at a time. All we do is stochastically simulate what the outcome might be. This is really the same thing we did in prior sampling. When we did prior sampling in a BaseNet, you can think of it as we had xt, the first variable, xt plus 1 as the next variable. You already sampled xt, and now you sample xt plus 1 given xt. Same process, exactly the same thing. If all we did was having time elapse and we had no measurements come in, then particle filtering would be exactly the same as prior sampling, because you would just keep going, xt plus 2, xt plus 3, and so forth. So that's how elapse of time works. Any questions about this part? Okay, then when observations come in, we saw that a good way to deal with observations is to do likelihood weighting. Now, get an observation. You now weight your sample by the probability of that observation given all the variables you have sampled so far. In an HMM, remember, if you say, well, let's weight, let's say we're at time 3, and evidence 3 comes in. If we're going to weight by the probability for E3 given everything we have sampled so far, which would be x1, x2, x3, E1, and E2, that's the same as weighting it by the probability of E3 given x3, just because of the conditional independence assumptions we have here. So likelihood weighting here comes down to just reweighting by this conditional probability here. That's all we need to do. So what happens pictorially is that when we cycle through these samples, for each one of them we look at the probability of the evidence given that particular value of the state, and we give each of them a weight. So 1, 3, we had the probability of the measurement was 0.1, and that shows up over here. But it stays in the same place. And same thing for all the other ones. Pictorially, what we're doing here is we're just scaling these particles up or down in size based on how much weight they have, so that you can read off more easily where there's a lot of probability and where there's very little probability in this distribution. Yes? So you need to look this up. So you have, when you're given an HMM, you are given 3 things. You're given the prior, px1. You are given the transition model, xt plus 1 given xt. And you are given the observation model, probability of the evidence at time t given the state at time t. So this is the table you're going to use where xt is instantiated by the particular particle that you're looking at. So for the first one, 1, 3 would be the value of xt. So far, if we were to keep repeating this, elapsed time observe, elapse time, observe, what we have is likelihood weighting in a graphical model or a BaseNet of this format. Yes? So for each particle, you look up in this particular table that you have, xt plus 1 given xt, but each particle, well, not necessarily, but many of them will have different values for xt, and so you will sample from a different distribution, because the distribution that you use conditions on xt, and so you'll be sampling from different distributions depending on what the current value is. So far that's likelihood weighting. When we looked at sampling in BaseNets, we said likelihood weighting isn't the best thing per se, because we're not accounting for the evidence that's still coming. So we're getting samples from this prior distribution, in some sense, not the right distribution. And so we might end up with a lot of particles with low weights that are kind of useless. And the way we fix it then is by running Gibbs sampling. And you could actually run Gibbs sampling in an HMM. It's just a BaseNet. But the thing with Gibbs sampling is that you keep resampling every variable infinitely many times until you finally get a sample. And in HMM, we're trying to keep up as things go by. And so we're going to do something else here to fix the likelihood weighting. So the thing we have to fix is that we might have a lot of samples that have a very low weight. And those are not great samples. They're not really representing where the ghost or robot might be. So in this case over here, we have this sample with very low weight. Well, that's not a great sample. So if we keep running likelihood weighting, we would keep propagating that, do computation for that sample, even though it's not that informative a sample. And that's what we're going to fix now. So here's what we do. We resample. And the idea here is that after you have your weighted particles, you think of this as a distribution over particles here. You have a distribution. You can sum this all together. Z equals, in this case, 0.5, 0.7, 0.11, 0.15. No, 1.5, 2.4, 3.3, 3.7, 4.6, 4.8, which is the sum of all of them. You can divide all of them by 4.8. You get a distribution over particles. Or you can, in that distribution, particles with a low weight will have low probability. And if you now sample from that distribution, what you end up with is a new set of particles where a lot of particles will land in the regions with high probability. So in this case over here, after resampling, we had the old P7, which is the green one, being resampled twice. It's possible you get one of them twice or even 3 times or 4 times. We get old particle 9 twice. We never get the old particle 4. That one just didn't get sampled because we sampled 10 times at random, and so not everything's going to keep being there. But the net result is that we now have 5 particles over here, which is reflective of the amount of probability mass we assigned to that particular region. So what we did is we got rid of the weights in some sense and put all particles on equal footing again by resampling and having now more particles where there's more probability mass. The beauty of this is that now, when we propagate again and we do computation for each of these particles are, in some sense, the set of particles is more representative of the distribution, and so we're better allocating our computational cycles. For example, we're not allocating any computational cycles to propagating from that particular square. We're allocating a lot of computational cycles to propagating from this square over here. You might say, why do we need 5? Well, maybe you could go in many different directions from that square because of the noise in the system, and maybe you could land in 4 or 5 different places, and now that you have 5 particles, you actually have a chance of capturing that when you sample from your transition model 5 times for that particular starting point. So that's the only difference between particle filtering and likelihood weighting, is this resampling step after every observation. And it's a way of reallocating your computational cycles to the parts of the space where there's more likely that, or more probability weight. Any questions about this? Yes? Good question. Typically, the number of particles will be much smaller than the size of the state space, and That's why we use particle filtering. And there are going to be a couple of quiz questions later, and I think we'll get into it. Let's get into it then and see if your question remains at that time. Yes? Resampling is the following procedure. You run through a loop, and you say for I equal 1, 2 through 10, and then you say new particle I equals to sample from this distribution up there. And that gives you the 10 new particles. Okay, so here's the overview. How it works. You start by representing your distribution with a set of particles. It could be uniform if you don't have a lot of prior information. If you do have prior information, put the particles where you think the ghost or robot might be. Elapsing time means just forward simulating, but it's a stochastic simulation. Loop through all your particles, stochastically simulate forward. When evidence comes in, you reweight, which means you have now weights associated with each particle. Then to ensure that your computational cycles at the next elapsed time are allocated in the right part of the state space, you resample and you get a new set of particles here that are resampled versions of the old particles, where particles with high weight will often appear many times, particles with low weight will often disappear. Okay, here's a quiz that a little bit gets at the question we had there. What can go wrong if your transition model, p xt plus 1 given xt, is deterministic? And as a hint, I suggest you think about the concrete example of localizing a ghost in a grid with just 2 particles. And think about what will happen if you try to localize a ghost with just using 2 particles as you go through this process if the transition model is deterministic. Let's give each of you a minute or so to discuss with your neighbor and see what you can come up with.
This transition model we're talking about. We're trying to ghost moving by its own.
The hidden Markov models.
Like
transition
ghost
model.
moving as it's moving. We're just trying to like predict where it's gonna be, right?
Yes.
It's our transition model, not the ghost. Ghost just moving.
It's the way we model the ghost, right? Just
but ghost moving by its own, right? On its
yes,
own.
but we don't know where it is,
Okay.
right? We have a model for how it tends to move. Just like in the Minimax search, you had a model for how the ghost would behave. The same thing over here, or in an MDP. Hey.
So, like doing the resampling to get rid of the weights, is there a certain amount to resample, or is it just like if you do this enough times and resample it each time, you'll end up numbers?
So you have a weighted set of particles. If you resample only once, you're not going to get a very representative representation of the distribution that you had. So you're going to have to resample as many times as you can within the time you're allowed, typically, so that you have as representative a set of samples as possible.
So each time you resample, I resample as possible?
Yeah, but typical implementations, you'll either fix it, or you'll have something that keeps track with some statistical error measure of how many you need to be accurate. All right, let's see what you came up with. Any suggestions of what might happen in this particular situation, which is a little extreme, but let's see what happens. Any suggestions? Yes? Okay, so a suggestion is, let's say your transition model, and we try to make it really concrete here, right, is one where maybe no matter where you are, what you tend to do is go back and forth. Maybe you go back and forth here, here. Maybe here you just kind of stay in place or something, right? And that's your transition model. And now if you start with a set of 2 particles, maybe one here and one here, then if the ghost actually started out anywhere but in those 4 squares, you'd never be able to adapt to that, because your 2 particles will be going back and forth. Maybe they'll be equally compatible with the evidence and you'll resample both of them. Maybe one of them is really compatible, gets a much higher weight. And then if you had evidence come in, this one got a really high weight, this one a really low weight, maybe at the next time you're stuck with this setup over here where you now have 2 particles here. And that's what you have as your model still. And now what will happen for all future times, these 2 particles will jump back and forth together. And when evidence comes in, because they're in the same state, they will get reweighted the same way. And you'll just forever keep having 2 particles go back and forth between those 2 states, no matter where the ghost actually is. It's pretty bad behavior, right? What is happening is you could measure as much signal over here as you can ever get that the ghost is over there. This particle filter would never adapt to that because it's stuck with 2 particles just going back and forth in that particular location. Any other thoughts about what might go wrong? Okay, let's build up on this then. So what's happening here is something very typical for particle filters and something important to keep in mind, which is that if you have a deterministic model, all that you can ever see happen in your particle filter is something that is compatible with where your particles started. So wherever you start your particles, there are potentially many simulation traces from there if it's stochastic, but if it's deterministic, then every particle has only one possible trace. And so if you have a deterministic system, all that will happen is you'll have these traces go on in parallel as time goes by. And then as you resample, some might disappear. And as time keeps going by, at the end of the day, you land with one of these deterministic traces as a thing that you retain, and that'll just be the thing you're stuck with forever. So in a deterministic model, particle filtering is pretty much guaranteed to do really, really poorly. So in practice, if your model actually were deterministic, you would put in some extra noise just to avoid this, such that your particles do spread out a little more. And that'll ensure that you get better coverage than you get with a deterministic model. Now, the models you typically get from us will be stochastic, but if you had, let's say, you would say, hey, I have this great robot, it behaves deterministically, I'm going to localize it. It's fantastic, no uncertainty introduced in every motion, I'm going to run this particle filter. Actually, you'll still want to use a model with noise. Otherwise, you're just stuck with whatever couple of starting points that you picked and the traces from there as your possibilities. All right, so that's one tricky part about particle filters, in that all you can see in the future is things that, where if you started, you needed to have started from somewhere that's compatible with it. So another thing people do a lot is just, A, you need to use enough particles, and B, you'll say, I'm only resampling 90%. So if I had 10 particles, I'm resampling 9 times, and the 10th particle I just generate uniformly at random. Put it somewhere. And that's a way to introduce noise and get a better coverage of the space. Gives you a better chance of, if initially your particles weren't exactly in the right spots, to still catch wherever the real probability mass should be. Okay, so earlier there was a question about what happens if you have a small number of particles. And so this illustrates the main problem with a small number of particles. It generally illustrates the points with likelihood weighting and particle filtering, which is that evidence never actually influences your samples in a very fundamental way. You just reweight things, might refocus your computation in this way, but you can never shift where you think things are based on the evidence. That's just the way they are. If you want to work with something that actually can shift the location of your ghost or robot based on the evidence, you'll need something like a more exact inference algorithm, or maybe something like a Kalman filter that really pushes things around based on the evidence. All right, robot localization. Let's look at some demos of really what I think made robot localization work was a combination of better sensors and particle filters coming around, people better understanding how to run them. Little things like, oh, you need to have enough randomness in your transition model, otherwise you stand no chance. Also enough computational cycles so you can populate the space well enough so you can actually recover the pose of the robot with reasonable likelihood. Let's look at some examples. What are we doing here? You'll see grids or maps that look like this. The robot could be in any coordinate that's unoccupied in that map. So it's a continuous set of coordinates that the robot can take on. Infinite state space. We cannot exactly represent the distribution over this infinite state space, so we represent it with particles. Initially, we populate this fairly uniformly, and then as the particle filter runs, we'll see where the particles tend to aggregate. That's where likely the robot is. Think of it this way. Let's say you're let loose in a building, and you don't really know which building you're in, right? And the room looks just like a regular room. Then you walk out of the room, and at that point, you know you're now in a hallway. You'll recognize that based on your measurements, and now all your probability mass will shift into hallways. Then you'll see maybe some particular things in the hallway that allow you to recognize some geometric structure that's particular to where you are, and then all of a sudden you'll realize where you are. That's the behavior we're hoping these particle filters will give us. So let's look at this one first. So initially, the probability mass is fairly well spread out. This shows, depending on what they did, this shows either where the robot really is because they knew it running the experiment, or it shows some kind of most likely estimate of where the robot would be based on these particles. Then as time goes by, the robot will move. We have a sonar measurement. So it's actually showing the most likely location of the robot based on the current set of particles, which is very uniform still. What's happening really is that the robot is keep moving in the same direction for a while. So that means it needs to be in a space where it's possible to move in the same direction for a while. Otherwise, this would have been very unlikely to happen. And so you see probability mass aggregate in the more elongated spaces. The longer it moves, the more it concentrates in the longer hallways. Now moved for a real long time, and only a few spots are still compatible. And then now it hits the end of the hallway there and gets some very specific geometric measurements and finds out where it is. Once it knows where it is, all the particles stay around the robot, and it can keep localizing itself very well. So the counter at the bottom left that you see in action is how many particles they decided to use at any given time. So they started with 40,000 particles. It's a lot of particles. But as time goes by, they're able to reduce it because the probability mass is all sitting in the same region. They say they can cover it with less particles. Yes? The state space is XY coordinates, so 2 real numbers. Oh, there's infinitely many states because, or as many, whatever many numbers you represent in your computer with a floating point or a double floating point. Whatever you prefer. Okay, so this is pretty cool that becomes possible. Here is another demo where there's a lot of symmetry. Starts in a room. And here as we, wrong one. As time goes by, we see that more probability mass in the hallway actually. So it thinks it's in the hallway now. It doesn't know yet where in the hallway because the hallway is fairly symmetric. There are a bunch of clusters of red dots where the probability is mostly localized right now. Keeps going. Still a lot of possible locations. At this point, 2 left. Then at this point, it decides to move inside this room. It doesn't know which room it's moving into. But once it's inside the room, realizes based on these measurements that it's getting that actually it's in the room at the top. And now it knows where it is, and all the mass is over there. And from then on, you can, in fact, use a very small number of particles to keep track of where it is. The measurements here are always laser beams or sonar beams shooting out and measuring how long it takes for that beam to come back. And then you reweight your particle by how compatible that measurement is with the location of your particle relative to the nearest wall in that direction. Any questions about these demos? Yes? Say that again? Yes, correct. So they assume you already have a map of the building ahead of time, you just don't know where you are. Now we're going to switch to not knowing the map of the building. So the idea here is that you say, I'm let loose in some building. I don't know what the building is. I just know it's, let's say I'm going to map it out in 2D because my sonar works in 2D or my laser works in 2D. And I don't know where I am in the building. I just know I'm starting somewhere. And as I go along, I want to make a map of the building. The representation underneath now, the previous one, the representation was XY was the state, or the state space was the XY coordinates. Now the state space becomes a lot larger. It was already infinite, but now it becomes infinite with more dimensions. We have the XY coordinates of the robot, and then for every location, maybe at a 2 centimeter resolution, it could be occupied or it could be unoccupied. So you have a really large state space. Every possible map, combined with every possible set of robot coordinates, is one instantiation in your state space. Imagine there's a lot of possible maps and then a lot of possible coordinates. There's no way you can represent a tabular representation of all of this. So let's see what happens if we do this. We have what you're looking at here, start from the beginning. Initially, all the particles are in the same spot. Just the way it's visualized, you can assume, if you don't know where you are, the idea is that, and you don't have a map, so nothing to reference to, you might as well assume that you start at 0, 0, and reference everything to where you started. So that's why all the particles are initially in the same spot. And as you go along, each of these particles has a location of a robot, as well as an entire map. And what's visualized here as the map is a superposition of these different maps, as well as a superposition of the poses of the robot in the superposition of the maps. So you get, effectively you have something about 30 particles here, so you also have 30 maps that are superimposed in a way that they're being aligned. And so the green dots are all the possible particles. The red is indicating the actual size of the robot in this experiment. In these experiments, typically a person will joystick the robot around and try to build a map of the building by just going around with the robot. It's sending out laser beams, and every time it reweights particles, it's based on how compatible the laser beam measurements are with the location of the robot in the map that it currently has for that particle. Now, right here is where the interesting stuff happens. So up till here, look at these walls. They're not really aligned. There's a lot of uncertainty about where you're at. When you're building these maps, when you come back to where you started, right, there's a lot of uncertainty of how exactly you traveled. There is some drift in whether you move left, right, forward, how much, and so forth. And so when you come back and you see the geometry of where you started, all of a sudden you realize how much you have been drifting as you went along. And so all of a sudden you realize which one of these particles is really the right particle. And you'll see everything all of a sudden collapse onto 1 or 2 particles, because those are the only ones that are compatible with seeing that geometry that you built up at the very beginning. So this is called closing the loop, and this is where a lot of the uncertainty will disappear. Get back to where you started. Realize only one of those particles really is compatible with what you had, and then now you continue building a map for another part of the building, and so forth. So you can imagine that when you run these types of algorithms, your particle filter to build a map and localize the robot at the same time, the bigger the loop you're going around, the harder this problem is, because the more drift you could have had, and it could be that you come around that loop and none of your particles is compatible with what you then see at that time. So typically you'd want to go around small enough loops relative to the number of particles you have available such that at least one of them when you come around is still compatible. Here's another example, showing it in a different way. So here again, you see the particles go around, the map being built. And then when it came around the loop, all of a sudden everything collapsed. And then now it has plenty of certainty about where everything is, and it can build a pretty accurate map. These maps can often be up to 5 or even 2 centimeter accurate with the current lasers and robot machinery and algorithms. So just want to look at the beginning again, just so you realize right when it's coming, right about here, it's about to happen. It comes back around to where it started. And of these many particles, only for a few of them will the measurements that it gets when it goes around the loop be compatible with what it had stored in its map. And those are the few particles that will have a high weight and will survive. Question here. So each of these particles has a map, not just a location of a robot, but also a map. And so at any given time, you move the robot in the map, so to say. You have a motion model for the robot, stochastic transition, a lot like the ghost in the grid, but continuous now. And then after that, you send out laser beams, and you see how compatible the travel times of these laser beams are with the map that that particle has stored. So each particle has its own map, and you see how compatible the measurements are. Based on that, you reweight. Now, as you haven't built a map yet, as you go along, it's always compatible in some sense. And the way the algorithms are set up is that they keep some part of the space as not determined yet, and they'll just fill it in the first time you get there. So the first time you get somewhere, you don't have to worry about compatibility. You leave the map empty there. But once you got somewhere, you start filling in the map for that particle. Then when you come back around and for the first time come somewhere where you already had measurements, either the new measurements could be compatible or they could not be. And so the particles which essentially modeled the drift in the robot correctly will be the ones that get the compatible measurements and will be retained because they get a high weight. Every measurement, you see how compatible the measurements are, and then resample particles based on their weight. Yes? Say that again? The reason it doesn't converge to 1 is because they introduce artificial noise in the system to make sure you get good coverage. So there will be a little more noise in the system than you actually need, than the actual model. And that will ensure that whenever you do the motion propagation, the elapsed time, all your particles will, even if you had one particle that had the highest weight, let's say you came back around, one at the highest weight, that was the one that won out, and all 100 resamples are that one particle. Then when you apply the motion model to these 100 identical particles, because the motion model is stochastic, you'll end up with 100 different particles at the next time. They'll be slightly different, but over time they'll drift apart. Yes? Yeah, so you'll keep sampling every time. You can be more clever about how much you sample, though. When you initially go around, you might want to sample maybe, keep track of 1,000 particles. But once you've closed your loop, you're going back around that same loop, you might be able to get away with just 10 particles and do well just with 10. Some people have found ways to do well with just 1 or 2 particles in some situations. Yes? So the transition model here typically is something where you say, I have a wheeled robot. I can control. It has 2 wheels and maybe a caster, but 2 actuated wheels, 2 big wheels. For the 2 wheels, you can ask how much they rotate. And so you say maybe 5 degrees on the right wheel, 5 degrees on the left wheel, but then because of slippage against a carpet or some tile, or because the motor doesn't actually rotate the 5 degrees, you don't move exactly how much as you commanded, and that's where the noise comes in. There was a question there. In this case, the map being displayed is the one for the particle with the highest weight. Yes. But in principle, there should be as many maps as particles, but then it's hard to see what's going on. All right, let's take a break here, and after the break, look at dynamic Bayes nets and speech recognition. All right, let's look at dynamic Bayes nets. So, what's a dynamic Bayes net? It's a generalization of a hidden Markov model. It's the same idea. You have a template, and you replicate it over time. So, you have a fixed set of variables that you might want to track over time. Instead of one variable, as in a HMM, there might be many of them, and you just repeat that structure. So here's an example that is not a, I mean, it's a pretty good model for what you're doing in your project 4. You have 2 ghosts. For each of the ghosts, you have a sensor that tells you something about where the ghost might be. Then, as time goes by, these ghosts could move. Where ghost A lands at time 2 depends on where ghost A was at time 1 and where ghost B was at time 1, because they don't want to move into the same spot. And then for ghost B at time 2, the location depends on where ghost A moved and where ghost B was at the previous time. So sometimes we get this kind of ghost A moves first, then ghost B moves, and this keeps repeating. And every time we can use our sensor and get information about where these ghosts are. This is a lot like an HMM. You can make this into an HMM. How do you make this into an HMM? You just define a new super variable like this. Here, right? Another super variable here. That just, the state super variable combines the coordinates of the 2 ghosts in one variable. That's now a 4-dimensional variable. And the evidence variable, super variable, combines both evidence variables of the original representation. But by making it into an HMM with these super variables, we lose the structure underneath. And it's nice to have that structure because it allows us to do things a little more efficiently. So we'll keep the structure now. And this will just keep repeating over time. We'll have conditional probability tables. We'll have a CPT here. We'll have a CPT here. Another CPT here. And another one here. And they'll be the same at each time. There's still a Bayes net. One that keeps growing as time goes by. You can run inference in this Bayes net by running, let's say, variable elimination. That'd be the same thing as running the forward algorithm in an HMM. You can also run sampling. Sampling is what we're going to look at, because the forward algorithm, that's just variable elimination on a Bayes net, so you know how to do that. Let's look at sampling. So now a particle is a complete sample for a time step. So an example particle, this here is one particle, has the coordinates of both ghosts stored in it. And as time elapses, we do a stochastic simulation for each of the ghosts of where they might land. That uses the conditional probability tables in this dynamic Bayes net. Then as we get an observation, we multiply together the probability of all the evidence variables given whatever values the particle had. So what we have here, this here, is whatever values for your current particle, you condition on that and evaluate the likelihood of your evidence. Multiply it together is a multiplication, and that's the weight of that particular particle. You could do this with 3 ghosts, 4 ghosts, however many you have. One particle would store all of them and would multiply together the evidence likelihood of all of them. Aside from that, just the same thing. After you've done that, you now have your list of particles. They're weighted. You resample to make sure you put your computational cycles where there's most probability mass, and then repeat. So implementation-wise, very straightforward extension of a regular particle filter. Just keep in mind that you run something where all ghosts take on a particular value for one particle. You can imagine doing something else, where you say, oh, I have 2 ghosts, I'm going to run 2 particle filters. You could do that. You could have 2 separate particle filters, one for each ghost. If you do that, what you lose is the interaction between the ghosts. If you have 2 separate particle filters, you'll not be able to model things like, oh, these ghosts like to move apart from each other. Or maybe they like to move together. Because once you treat them as separate particle filters, you cannot capture that interaction anymore. So the reason to put them all in one model is because then the interaction is encoded in This guy's CPT and this guy's CPT, same here and here and so forth. Question there? Yes. Which particle? This here? That weight represents, if you had run likelihood weighting in the basenet that goes up, that just has an elapsed time part and then an evidence part, that would be the weight in the likelihood weighting for that sample. That's what that weight is the product of the evidence variables, the probability of the evidence variables given their parents. So it's exactly the same as in likelihood weighting, just for this particular type of basenet. It depends on the exact structure what this means, but it's the probability of the evidence variables given the variables that you sampled in this case. All right, so now let's switch gears. We know how to run HMMs, do inference in them. Sometimes the type of inference you want to do is not the type of inference we've looked at so far. Imagine something like speech recognition. Maybe what you're interested in is the most likely sentence that was uttered, not a distribution over all possible sentences with a weight for each possible sentence. Right. Answering that type of query, find the most likely explanation. That's what we're going to look at now. So how does this work? You still have an HMM. You have states, observations, an initial distribution, transition model, emission model. The new query we'll look at is find the argmax of this expression here. What is this saying? It's find the sequence of state variables such that given the evidence, that is the most likely sequence of state variables. There are a couple of ways of doing this, but let's first look at what this actually involves. Let's unwrap this HMM and say, well, what's really going on? We have a sequence of state values. At time 1, it could be sun or rain. Time 2, it could be sun or rain. And between those times, we could go from sun to rain, rain to sun, rain to rain. For each of these, there's a probability. There's a probability of S given S. There's a probability of R given R, and so forth. Right? A particular sequence of values, let's say sun, rain, rain. You thought, well, that's a sequence. You can evaluate the probability of that sequence given the evidence. How? Well, the probability of that sequence is you multiply the probabilities on these transitions together, right? That's how likely it is to follow that sequence. And then if you have evidence, you also multiply in the probability of the evidence given those instantiations. So you multiply in here, you multiply in probability of evidence given sun. Over here, you multiply in probability of evidence at time 2 given rain. Here, probability of evidence at time 3 given sun. And here, the probability of evidence at time 4, or n, given rain. So if you multiply those all together, what you're really doing is you're multiplying together things of this type. xt given xt minus 1, and et given xt. There are many sequences through this lattice, and finding the most likely sequence of states given the evidence comes down to looking at all of those sequences and finding the one that's the most likely one. That one that gets the highest score, where the score is the product of all these probabilities. So the naive thing is you enumerate all possible sequences. In this case, if there's sequence is n steps long, it'd be 2 to the n possible sequences. It's exponential, so it's not great. An alternative is to say, well, this is really just a search problem, right? We're trying to find a sequence of states, and we try to find the optimal sequence of states. And for every successor call, this is the additional, in this case, reward that we're getting because we want probability to be high. And we try to find the sequence of states that maximizes the product of the probabilities that comes in at every time step. You could run search, you could run A-star search. That's actually done for a lot of these problems if they have a very large state space. Another thing you can do is to run the equivalent of the forward algorithm. which is a dynamic programming algorithm. And what that does, we're not going to get into the details, and we're not going to expect you to know the details, is the forward algorithm looked like this. And rewritten here with factors, you have a factor at time t, which is the joint probability of xt and all the evidence, is written as a function of this thing here, which is the probability of xt minus 1, given the evidence up to time t minus 1. That's just the forward algorithm written out again. If you want to find the maximum as opposed to the probability summed out over everything, we just replace the sum with a max in all of these computations, and we get the same algorithm. We just, wherever we had a sum before, we now put a max. You had a loop to sum something together, you now loop and compute the max. So algorithmically, we get something pretty efficient here running this algorithm. We get something that scales linearly with the length of the sequence rather than exponentially. All right. We haven't seen the specifics of this, but think of this as a new primitive that we have, and if we can now model speech with a hidden Markov model, then we can run this algorithm to find the most likely sequence of words that was uttered. So let's see how we can model speech. Remember the example from the first lecture, the goodbyes. That's what we're going to look at. How do you recognize speech? Well, what is speech? It comes in as a sound wave. So how do you capture that? A simple microphone would be something where you have a membrane. When the air pushes against that membrane, the membrane will move accordingly. The membrane might have a magnet attached to it. Then the magnet will move accordingly. Then if you have a coil sitting around that magnet, then the motion of the magnet will induce a current in the coil. That current in the coil you can measure. And then that measurement is representative of the amplitude of the signal at that time. This is how you go from this continuous sound wave that's actually living in the air to something in a computer. Once you did that, it could look something like this. Here's your sound wave. That's what the computer gets to see. All right. Who wants to recognize this? What is this? What is this saying? Hello, world. That would have been a good one. That's not what we put in here. I guess Pac-Man would be another guess, but that's still not what we put in here. Well, it's hard to guess for us. And it gives you an idea of why it might be hard for a computer to understand what's being said, even though for us it's very easy to understand speech because we're trained to understand it. But this is what the computer gets. What this was Speech Lab. What you see here is some very interesting things. You see, for example, here you get the hissing sound of the S. Then here actually you get nothing, because even though we might hear a P, you only hear the P once you start the next vowel. And so it's actually quiet for a little bit, and then only you realize that there's a P, which is really only shown over here, and so forth. So it's a pretty complicated problem. Looking at this, you could say, well, how do we build an HMM around this? Well, we want to consider this our measurements, but maybe they're not the most effective measurements to work with. So maybe we can look at what the human ear does and work from there. What does the human ear do? Well, it says, I have essentially a filter bank sitting here. Get that sound wave coming in, and there'll be neurons sitting there, each neuron attached to a particular filter, and that filter picks up on a certain frequency. And so neurons will spike based on which frequencies are present in this sound wave. So we could do the same thing. We know how to do that to extract frequencies. You just run a Fourier transform. That'll tell you what frequencies are present in your signal. So you get out the Fourier transform for small windows, like that. And what you see here is, as a function of the frequency and time, the denser the plot, the darker it is, the more energy there is at that time in that frequency. That might be a better representation of our measurements than the original sound wave. That is actually what people use in speech recognition. So your evidence variables are how much each frequency is present at a given time. They're continuous, but you could discretize them, make it work. All right. So how does sound actually work if you look at it? Here is one vowel, part of lab, the A part. What do you see? You see a lot of repetition. And so you can see that most likely just picking up on whatever are the dominant frequencies in a particular part of speech will tell you what you are listening to. If you look at the spectrum here, where is the energy? There's a lot of energy here, more energy here, more here. See something that's shaped like this. All right. Now, how does this get generated? Why do we have some intuition of why this would be the shape? You have your lungs. They push air over your vocal cords or vocal folds. What they do is they just kind of oscillate back and forth, and you can make them oscillate at different frequencies. You pick some frequency, that's the base frequency of the sound that you make. Then the system around it will make that into many, many frequencies. So you pick your frequency, and every integer multiple of that frequency will be generated. Then as all those integer multiples of that frequency travel through the rest of your head, your mouth, your throat and your mouth, you can reshape the cavity is going through by moving your tongue, moving your mouth. And by doing that, you filter out certain frequencies. Some will be retained, some will not be retained. And so you apply a filter, maybe one that looks like this for the ah in lab. And now you get out something that looks like this. So that's how it works mathematically. All right. A simplified model is one where you just think of your speech generation system as an open tube. Here is where a sound comes out. Here is where it starts. And the length of that tube will determine the base frequency of which all the integer multiples will be present. And you can modulate that with your vocal cords, and it's exactly how your mouth is set up. And then your mouth will then later filter over it to get the precise sounds that you want. Now, if you look at this, throat, however long your throat is, decides the base frequency, could be longer or shorter, and then here you get the filter. Now let's look at some different, so what we look at here is the sound E, recorded multiple times, but with different base frequencies. So this part could be very short, gives you a low frequency, and every integer multiple of that low frequency will be present. You can make it really long. You get a high frequency as your base. No, the other way around, sorry. Very long is a long wavelength, so it's a low frequency. This is large lambda, low frequency, and this is short wavelength lambda, so high frequency. So if you vary the length of the first tube, or you say the same sound E, what you get is actually the same pattern, because your mouth is still in the same shape, and so that filter still acts in the same way. But you can see that once you land over here, where you have a very high frequency as your base frequency, because all you get is the integer multiples, it's much harder to extract the form of the shape in the frequency spectrum. Right here, yes, it's still compatible to draw something with 3 bumps, but there's a lot of other stuff that would be compatible with what is just shown over here. That's why, let's say you go to the opera, somebody's singing there at a very high pitch. It might be much harder to understand the words they're saying, because at that high pitch, you get much less signal about the exact frequency filter they're using to form their words. That's how it works. Robot performance. Now, you slice this into acoustic features. When you say a particular sound, you might say it for a varying amount of time. And so you'll have, for any kind of sound, you'll have multiple time slices in discrete time. Our hidden states X are what phoneme you are in the process of pronunciating or listening to. So we have an emission model, E given X, which is what frequencies might be present as a function of the phoneme. Then we have a model that models what will be the phoneme pronounced at the next time, given the phoneme you're pronouncing at the current time. That model will put a lot of weight on it being the same one as the previous time, because usually the same one goes on for quite a while. So we have a very large state space here. We have a state space that has one state for each sound, right? But then we want more, because we don't just want to recover which sounds were being made. We want to recover which words were being said. A state variable doesn't just say which sound is being said right now. It also says in which word you are currently. Okay? So we have for each sound in each word, let's say there is maybe 200,000 words, maybe 100 sounds, then there is 200,000 times 100 different states. Now, we can build a state graph, a transition model between these states. So what we have here is we start pronunciating something. We go to the first. We say, let's say, the word need. We start by going into a state where the letter N is pronounced. We might stay there for a while. And the probability here, A11, tells you the likelihood of staying in that same state. Then whenever you're in this state, you get emissions based on some probabilistic model that you build of which frequencies tend to be present with how much weight for the particular N1 sound. Then at some point you might transition to the new state over here. Again, now you have a new model, the E sound, whatever is the model there of likely presences of frequencies will be stored in this model over here. Same here, same here. And this will store somehow how likely yours continue in that same phoneme or would skip to the next one, and so forth. So this is here. This is a conditional probability table, but you show a lot more structure in this graph than you could by just showing a table with a lot of entries, among which a lot of them would be zeros. Now, you know that certain words are more likely to occur after certain other words. I mean, that's what grammar and semantics tell us, right? So you can say, well, after I finish the word, I'm in a state that says I finished the word 1. Then I can transition to the beginning of maybe this word, but also maybe this other word here and any of these other words in between. And so by encoding both the word and the phoneme you're in, you can really model the statistics of which words are likely to come after each other. If you thought the next word really depends on the past two words rather than just on the past word, then you would build a bigger state space where you now store in the state the current word, the previous word, as well as the phoneme you're in, and then you can encode that the next word depend on the previous two words. If you think it should depend on the previous three words, state space blows up even more. How do you get these numbers? Well, you just make counts. So maybe you crawl the web, you check after the word the, which other word appears? Well, you found some, let's see, 23 billion occurrences of the, and out of those, this many times here, first was the next word, and so forth. And then you can say, for door to come after the probability is 0.0006. All right, so the decoding is just a matter of running Viterbi. A lot of speech recognition these days, it might be available on your phone, but it actually might not run on your phone itself. Often, the data gets sent off to the cloud. They'll run Viterbi decoding or a star-based decoding, find the most likely sequence of words, and send that back to your phone. Okay, two things here. One of them is what we just looked at for speech recognition is a first example of a set of things we'll look at. In the future, we'll look at robotics, vision, and language processing, where it's more illustrative than meant for you to understand all the details. So speech recognition, we're not going to ask you serious questions about speech recognition, probably no questions at all, in fact. It's just to illustrate the concepts that we've covered in an application now that we're ready to do so. In terms of context where we are, we're done with part 2 of this class. So we know how to do probabilistic reasoning. The last part is, well, we've looked at how to make decisions if we had a model. We've looked at probabilistic reasoning, which allows us to reason with probabilistic models. We haven't seen yet how we build these probabilistic models from data. That's what machine learning is going to be about, and that's the remainder of the class in addition to more applications. See you next week.